Macy, we got a test on.
Yes, yep. It's done. And my activities are with it.
Okay. All right, so celebrate quickly on your chapter 7 because we're working on chapter 8. And basically, so this we're moving through 8 the rest of this week, and then we have to look at 9, and that is just a quick little like take-home type quiz. All right, and there's not even a home fun, like there's an optional home fun, just like a single activity. All right, but basically we have like week and a half plus a lecture, and then we got a couple of free days, which we'll do some what I call enhancement material. So nothing tested on, optional show up days. And then I was like, we have our final in just a few short weeks. So we were in chapter 8. I was like, we were in chapter 8 at this point. And we'd already got through some initial stuff all about vectors. And then we're going to continue everything with vectors. And one of the biggest things you do with vectors is the dot product. So the dot product, because vectors, right? So understanding the definition of a vector. A vector is something with a magnitude and a direction, all right? The idea is that it is a line segment, okay? It has a starting point, it has an ending point. Now, when we start getting into 3D, visualizing that is a little bit tougher, but that's why we need to rely on the math part. So with this three-dimensional vector or multiple three-dimensional vectors, we can create two different things, the dot product and the cross product. Two ways to multiply vectors because they have a magnitude and a direction. And so the dot product takes into account just the magnitudes and represented by the little dot in between them. Why this is nice is because we have two vectors out in space, and so we can find the angle between them, right? This is trig. We're always interested in finding the angle between them. So it's got this nice little formula, all right? The dot product over, all right, the magnitude of each vector results in the cosine of the angle between them. Now, sometimes we just find the cosine of the angle. Sometimes then we find the entire angle because if you get the cosine of the angle, in order to find the angle, what last operation do you need to do? Inverse cosine. Inverse cosine. And you can be in either degrees or rads, right? As long as you're consistent. So when you have that, then you can take the inverse cosine and we can actually find the angle in its entirety. The dot product is nice because it can identify orthogonal. Orthogonal is just a fancy way of saying perpendicular, right? But this is terminology we want to get familiar with. So perpendicular, orthogonal, all fancy ways of saying what kind of angle. What does perpendicular mean? 90 degrees, right? A right angle. All right, it is just another way of saying a right angle. And the math would work out here because 0 over whatever doesn't matter. So the inverse cosine of 0 results in 90 degrees, pi over 2. All right, so this actually helps us identify without going through that whole operation. I can just do the dot product and identify if these two lines out in space, which will be hard to visualize, are at 90 degrees or not, or whatever degree they are at particularly. And then lots of properties of dot products. that the order doesn't matter because it's dealing with only the scalar piece of the operation, just the magnitude part, all right? And you can multiply values in and out, all right? So all the operations that you believe occur do occur, all right? The biggest thing is that when you result, all right, when you do the dot product of something, it ends up just being a scalar, all right? So, right, the magnitude squared, all right, that is just a number, all right? So dot product results in just a number, just a magnitude, or just a value. So let's look at an example. So I have the vectors, all right, u and v, all right, given in the ijk components. And I want to do the dot product. I want to find the dot product of the two of them to start. Which means you take each piece and multiply them. And remember, with adding vectors and multiplying via dot product, at least, X components go with X's, Y's with Y's. All right, so make sure you keep the values, right? So that's actually 1 times 6 plus -2 times 3 plus -2 times 2. And results in just a value. And I want to find the angles between the two vectors, which means I will also need the magnitude of each of them. And then we can use our formula now. And since we're back in degrees, I was like, typically for a lot of the stuff we're gonna do, we're in degrees, right? Got to be able to go back and forth between radians and degrees, keep track of that, right, Galen?
Oh my gosh, yes.
That was painful.
It was, right, yeah.
I was like,
I apologize, but.
I was like, no. I was like, painful to you, because I've done it too. I was like, always check your mode, right? Oh my gosh, it's just like, oh no. All right, and it doesn't matter. You can do, okay, some of those formulas do, and we got to watch out because some formulas use degrees, some formulas use rads. This I could come out of and I could be in degrees or rads, wouldn't matter, okay? Okay, and then lastly, right, so determine if the vectors are orthogonal. So the vectors are orthogonal? No, why not, Brenna?
Is it not 90 degrees?
Because it's not 90, it's literally that simple, all right? I was like, you're like, yeah, no, it's literally, that's 100, gosh, it's 190? No, all right? All right, and it is that simple, all right? The vectors are not orthogonal since the angle between them is not 90 degrees. Also, all right, we know the dot product was not zero, because that's kind of a dead giveaway immediately, all right? So you can also say the dot product, I knew it up here, all right? They weren't 90 degrees because the dot product was not zero. Another big thing with vectors, all right, and vectors typically represent force. So, right, force has a magnitude and a direction, all right? We did some of this last time. The whole idea is that when you apply a force, you apply it in a direction, because no matter how much power there is, you need to point it somewhere. So vectors represent force often. That's why you see this so much in physics. A vector projection means you are applying the result of one force onto another, right? The force I push on this table, all right? And that, the movement of that table, that's the vector projection. Because it's the force that I applied that results in another direction. And so, all right, it's got a little formula. Now, here's the big thing, all right? Just what I did on the table, right? When I push the table, that table is moving, all right, in a direction. That means that is a resulting vector as well. How much force I applied, my magnitude, then moves that table in a direction, which means the resultant is a vector. So notice that this will end up being a scalar, this calculation, all right? But then it results in another vector, all right? So the output of this, all right, of a vector projection is always another vector. And then I could identify the scalar component, right, which is just this piece. And so to that end, I want to find the vector projection of u onto v and the scalar component of u in the direction of v. So just so we can see a visual here. And two possible options, all right? So the one I was showing was a downward one, all right? But you have the vector u being in an upward trajectory, and then that projection then pushes and moves v, all right? Similarly, they can be in opposite directions, okay? So the angle between them, all right, is what the actual data that we're looking for, and the projection is, you know, pulling them backwards. So lots of different possibilities of what can occur here. Now, the good news for us, all right, this is the vector projection of u onto v. So make sure, all right, by definition, u onto v. So if this is f onto w, make sure you replace all the variables appropriately, right? Again, a general equation. And this is one that I always have to use the equation directly as well, all right? So dot product first. Magnitude of v. And you could do those calculations slower, but they're not hard. And then that whole thing is being multiplied by the vector v. So whatever number this results in, then it multiplies into each component of our vector. And congratulations, Jada, on the quiz. She got the high score. I mean, so far. Macy might have beat you. I was like, we found where you're really strong, huh? I was like, application, which is what we're still in. All right, which we're in the rest of the semester. Okay, and then calculate away again. There's not much to these calculations except just watch your formula. So calculate away, all right? And then multiply each piece through. And similarly, the scalar component. And look, oh, are these the same vectors we had? And then the scalar component, again, by definition, scalar, all right, no direction, all right, not a magnitude, just a value that is calculated. All right, so pretty straightforward calculations. Again, much more commonly used with force. And we're going to look at an example of that. One of the big concepts that we do is we break vector projection, and this is especially true with forces because we like to break forces into a parallel piece, all right, and an orthogonal piece. What does orthogonal mean again? Macy?
90 degrees.
Right angle, yes. Okay, so by definition, a parallel, one that runs parallel and one that is perpendicular to that. So it breaks the vector down, all right, into two pieces. And that is very, very common in physics because in physics, we're always trying to get to find some angle that has an x component and a y component. V. And so, all right, I have, right, this is the definition of vector projection. Oh, whoops. Oh, shoot, I did write that incorrectly. I apologize for that. Squared. And so, all right, when we have the projection, all right, is the parallel piece because whatever your vector is, that is, all right, parallel to that vector. And then we have a right angle piece, all right, which is really just the vector u, whatever that is, minus the projection. And that breaks it into a parallel and a orthogonal piece. So along those lines, all right, I have a force F, all right, is applied to a spacecraft, all right, with a velocity vector, all right, forces and velocities, physics all the way, all right, express F as a sum of a vector parallel to V and a vector orthogonal, all right? That is vector projection all the way. But notice, did it say vector projection? No. Okay, so a lot of times you see it, all right? But when it's saying, right, applied to a spacecraft, when force is applied to something, that by definition means that you're projecting it, you're moving it, you're adjusting it. Okay, so it doesn't always say vector projection, but definitely when it says break it as a parallel and orthogonal piece, all right, that should imply vector projection. Also, right, when force is applied to anything, basically, okay, that becomes vector projection as well. All right, so that means we want to write our vector as the projection of F onto V. And so adjusting our formula and then calculate away. Oh, and actually I had this above. The magnitude squared, I mean, by definition, magnitude is just u dot u. It's dot itself since each value is being squared. So, and then square root the whole thing for the magnitude in general. So actually, if you have the magnitude squared, you can just do the vector dot itself, right? Which is each piece squared. Just a fun fact of dot products. All right, so each piece and this does bring up one thing. So we're in 3 dimensions. We have IJK, right? That means X, Y, Z. For our velocity, right, we have 3I minus J. What's the K component? 0, right? So, right, don't forget that that always exists. Even when we're just looking at IJ, right? The K component is there. It's just, it's 0, right? You could still be in 3 dimensions and just looking at 2 dimensions. All right, so the K component 0, and then V dot V. Now, also note, I'm writing these in IJK component form, but you can still, you can switch all the way to our, whatever, our vector component form, right? Remember with those, the hard brackets. So if you prefer that one, whichever way you prefer to multiply, that is completely up to you. Okay, and then we're doing F. All right, minus that same calculation, 6 minus 1, 5. All over 9 plus 1, 10. All right, and then close it, because the whole point here, okay, is this is one calculation, this is one calculation, right? We are keeping this as a parallel piece and a perpendicular piece, all right? I don't want to combine all those, so I want to result in two vectors. So I have an X piece, I have a Y piece, right? Now, be aware too, okay, 3/2 I plus 1/2 I, that makes 2I. Negative 1/2 J plus 3/2 J, oh look, that makes J. So if you keep going, you end up with a vector F. That's the whole point here. This has to result in the vector F, right? It was coming up with those components that requires the projection. But we've identified this as a parallel piece and a perpendicular piece to our vector, to the projection. All right. So I was like, basically it was a lot of work to undo, to rewrite a vector that we already knew. All right, we didn't actually change anything here. The vector that is being projected was this piece, right? By definition, that is the vector projection. So that is the vector that results from F onto V. All right. But we've only just written it, all right, as a piece of X and a piece of Y. Well, okay. It was like, just kind of, it's calculating away. I was like, but vectors are just such a big thing, all right? And if you've had physics, which probably all of you have, all right? And if you're continuing into physics, all right, this becomes a huge deal. We good?
Thanks.
No problem. All right, so vectors in space. So again, we've already been looking at 3D a little bit. And the biggest thing, and here's, I was like, I know that math seems, it's kind of cumbersome and everything. But it's like we showed in the beginning, when we have 2D vectors, you actually can line one vector up and put the next one next to it and next one next to it. And where the first vector started and the last vector ended, that's your line. That's the sum of all the vectors. When you get into 3D space and you add 3 vectors, I don't know, like this vector, I'm not sure what that one looks like. And then when I add another one on, I'm not sure how that looks. So this is why we use the math. Because at that point, all right, I can't just draw them out and then line them all up. All right, it's nice when you have 2D vectors and you can do that. But once you get to 3D, we have to actually start trusting the math. Along those lines, so you'll see some same formulas with different terminology. And a big one is distance, the distance between 2 points. This formula, again, should look super familiar. What does this formula look like? We should definitely recognize this. It's a slightly more complicated version of what right triangle formula? What? Pythagorean theorem. This is just the 3D expansion to Pythagorean theorem. All right. W equals x squared plus y squared plus z squared. That's all this is. This is also the magnitude formula. Okay, this is how we calculate magnitude. So Pythagorean, magnitude, distance, it's all the exact same formula. All right. And so there is a lot of verbiage that we're going to be grinding through, but the calculations don't get any more complicated. All right. And no matter how complicated the formula looks like, it's still just undoing Pythagorean. It's literally the thing that we all knew before you got to this class. All right. We're just expanding it to 3D. And so the calculation, so distance, and then terminal point minus initial point, squared plus terminal point minus initial point. Actually, that doesn't matter because of the squared, but for consistency. And calculate and get a value. And I don't have, distance is a one-dimensional value, right? So it's not units squared, just units. All right, but again, magnitude, Pythagorean, distance, all the same formulas. Something else that you ideally have seen to some degree, maybe you didn't do it heavily in algebra, but circles. Does anyone remember the equation of a circle? The general equation of a circle? Like a circle with radius 1? Like, might have been a while. Our most generic circle, x squared plus y squared equals 1. All right, so you might be a little rusty there. And that is the equation of the unit circle. X squared plus y squared equals 1. That is the equation of the unit circle. Expanding circles to spheres follows the same pattern, all right? And we can then shift it. So this is the unit circle, which means the origin is at 0, 0, all right? But if you want to have a sphere, so now we're in 3D, all right? With any origin, you just adjust, all right? Minusing that value off of the quantity squared of whatever x, y, or z dimension that is. And then this unit circle has radius 1 because it always has the form a squared. So in order to make a radius of 2, this would become a 4. So basically the general equation of a circle expands to a sphere. All right, so 2D to 3D is actually pretty simple stuff. All right, it's really just about remembering what was the generic equation of a circle and then expanding that definition. This is also stuff that we should recognize from, well, our graphing in here and graphing polynomials in general, right? When you subtract the value on the inside, it moves it in the opposite direction on x, right? Do we remember that? So we did that in here when we did our graphing chapter. Okay, so the point is this. So I have this equation, this generalized equation, and I want to find, all right, the center and the radius of the sphere. So my very first step is let's organize our x's with our x's and our y's with our y's, z's with z's. And while I'm at it, I'm going to put that 1 to the other side. Okay, so I put all my x's together, all my y's together, and all my z's together. All right, and then I just move that 1 to the opposite side. Once I have this, okay, so I already know, all right, at least the y coordinate of the center of my sphere. What is it?
0.
It's 0. All right, because there's nothing involved with this. So this is actually generically of the form y minus 0 quantity squared. So I know that one's done. These ones are a little bit tougher because they don't have quite this correct form. All right? They don't have quite this correct form. So ignoring everything else that's going on, just looking at x squared plus 3x. In order to get it into this form, x minus number squared, how do I adjust that to this? Does anything spring to mind? Do we remember going way back? Tangent. Y equals ax squared plus bx plus c, going from standard quadratic form to what we used to call vertex form. Do you remember how to get something, a quadratic, to vertex form? Okay, let's back up further. How do you solve a quadratic? There's 3 techniques. How do you solve ax squared plus bx plus c equals 0? What are the 3 techniques to solve it? Factoring. That's the best one. What are the other ones?
Quadratic equation.
Quadratic formula. That is, I know the terminology is funky. This is called the quadratic equation and use the quadratic formula to solve a quadratic equation. Okay, but yeah, okay. Quadratic formula and factoring, those are the top 2. There's a third one. Does anyone remember what it is?
Square.
Completing the square. And that's how you transform a quadratic equation into vertex form, standard form to vertex form. So we need to remember completing the square. So, and in this case, we need to complete the square for the x's, we need to complete the square for the y's. So we have to do them individually. All right, so let's refresh on some of the things you have to do with completing the square. So for a quadratic equation in standard form, in order to complete the square, the a term has to be 1. Now, good news for us, z squared, y, x squared, they're all already 1. All right, so the term next to the quadrant, the squared piece has to be 1. Now, if it's not 1, all right, you have to factor that out. So in our case, no problem. We don't need to factor it out. Then the big thing is you identify the b term. We identify b, and I like to go all out here. Then I identify b over 2, and then I identify the c term, which is b over 2 squared. Okay, so for our first one, all right, and when I'm talking a's and b's, I'm talking about standard quadratic form. So a is 1, all right, what is the b term? 3. Okay, so b is 3. b over 2 is 3 over 2. Oh, okay. Then b over 2 squared is 9 over 4. Okay, so we identify b over 2, and c. And that c term, add to both sides. Now, we have an equation here, so I can add it to both sides. If you were just had an expression, then you'd have to add and subtract it. That way you'd be doing 0. But this one, I actually have an equality. So I'm going to add 9/4 to this side and add 9/4 to this side. So again, I'm not changing anything. If you do it to one side, you do it to the other, nothing changed. Okay, good. That one's done, and we're going to come back to that in just a minute. So now let's do the z's. And we start that process again. So, all right, A equals 1, check. What's the B term? -4, all right? Make sure you pick up that sign. So -4, -4/2, which is -2, and -2 squared, which is 4. And again, add to both sides. So +4, +4. Okay, so I have all these pieces, right? Now I need to actually do what the whole point of completing the square is. Okay, and -1 + 4 + 9/4 is 21/4. All right, so I'm just adding those three numbers on the right side of my equation. So the whole point of completing a square is to get it into the form of x plus something. And similarly, z plus something. So the reason I like to write this piece out here, so this was the x's one, is that it always ends up being x plus what?
B/2.
The B/2 piece. It's always, because when I look at this, can you clearly see that that's x plus some whatever squared? No. The point of writing those steps out is this is always x plus B/2 quantity squared, always. Because that does factor, that's what's called a perfect square trinomial. So it factors perfectly. But 9/4 is a horrible value, all right? This one you should be able to see. This is z minus what? Z minus what quantity squared? 2. Z minus 2. And I can clearly see that because 2 times 2 makes 4. This one I have to look and be like, gosh, what times what makes 9/4? And that one's actually still not bad, it's 3/2. But it doesn't matter because B/2 3/2, B/2 -2. By identifying that, this piece is always the B/2. It's always variable plus B/2, as long as you completed the square correctly. Okay, so let's start actually. So we have a sphere, it has a radius and a center. Let's start with the radius, because actually the radius is pretty easy to identify. If this value on the right side of the equation equal 21/4, the radius is always that value square rooted. So that means the radius is square root 21/2. All right, because this is the radius squared on the right side of the equation. Then the center, now that I have this in the proper form, the center is just the opposite sign of all these values. So that means the x coordinate is -3/2, the y coordinate is 0, we identified that one first, and the z coordinate is 2. So, well, this is not really a trig concept, except that we're extending this to 3 dimensions. This is an algebra concept, right? And completing the square is something that you really need to make sure you're good at, right? Because it just keeps coming back. No matter how far you get, And I know that we focus on factoring so much because factoring is everything, factoring is everything. But completing the square, all right, there's a reason that we teach all three methods, okay? And completing the square is a big one because when you have a bunch of variables, you can't quad form this, all right? Need to make sure that you have a technique for completing the square. All right, are we good there? All right, so additionally, we can find directional angles in 3D just like we did with the dot product in 2D. So when you have u dot v, right, and you can find the angle between them. Well, similarly, with a given vector, I can find the directional angles off of each axis. So where that vector is off of the x-axis, where is that vector off of the y-axis? Where is that vector off of the z-axis? So this is actually more of a bearing idea, right? Because we remember when we talked about bearings, okay, it comes off of the y. Well, this is bearing in 3D. How far off of the x, how far off of the y, and how far off of the z? Oh, got messed up. X, y, and z, right? So how far off of the z, how far off of the x, how far off of the y, right? And we can identify that the vector's angle between all three of the axes. So along those lines, for a given vector, because again, I was like, once I'm in 3D, I was like, we start having a real problem, right? Can everyone visualize this? It's pretty tough, right? Okay, so, right, and you have to set up, okay, so here we are. I'm on the X, so I'm 3 back, okay? And then I'm 2 over on Y, so that's gotta be my Y, right? And then I went down. Oh man, so I went the wrong way. All right, so it's actually, so that was my origin. It's that. Oh, there we go. All right. So that's why, again, my point is we trust the math. So in this case, I can find the directional angles of each case. Cosine of alpha equals, let's find the magnitude first. And the A component, all right, is just the X component, right, by definition. So it's the X component, the Y component, and the Z component. And we can find the angle off of each axis. And it is pretty simple calculation, but the concept is that that's how far, all right, to ideally help us draw the vector off of the axis. And actually already given that, oh no, so it would still be off of the positive Z axis, so it is up. So since that one was negative and that one was negative, right, the X and the Y components, all right, since it was in the negative direction, all right, off of the positive X axis, it's an obtuse angle because it's further than 90 degrees, right? So, And then there is a nice property, and this formula actually should look familiar. All right, so if we have the directional angles, all right, then the cosine squareds of all the angles equals 1. What does that look familiar to? No one knows what that looks familiar to? That is a good guess, but no. I mean, sort of.
The fundamental.
The fundamental. All right, this is the fundamental extended into 3 dimensions. All right, in 2 dimensions, the fundamental x represents cosine, y represents sine. But now we're in 3 dimensions, we're actually using cosine off of all of them because each one is its own individual x-axis. All right, so this is basically the fundamental identity in 3 dimensions because we're starting on the positive, right? The positive x-axis, positive y-axis, positive z-axis. All right, there is no third trigonometric function, right? If x is cosine, y is sine, tangent isn't z. Okay, it's important that we understand that, right? So this is basically just the fundamental identity extended into 3 dimensions. And that does give us some nice properties that we could then mess around with. So the vector v makes an angle alpha with the positive x-axis, angle beta, all right, with the positive y-axis, and acute angle gamma with the positive z-axis. Find the missing angle. Oh, so then I can use our extended fundamental theorem. And it didn't specify, but this is in radians. Hopefully that was implied. When I plug in what I know, and then I can do cosine of the angle. And I mean, that's a number, minus, subtract those from 1, square root the whole thing. And we should get gamma equals pi over 4 reds. I was like, the formula is as simple to use as the fundamental theorem was. And the difference now is, oh look, we actually have numbers. One other extension. So with the directional angles, we can break them down into a vector into its magnitude and direction. And this is what we were looking at last time, because this is another very common thing, right, in physics. And this actually corresponds back to the concept a unit vector. The directional angles always actually end up making a unit vector, because by definition, cosine ranges between -1 and 1, right? And by definition, a unit vector is a vector divided by its magnitude, which are a bunch of values squared and square rooted. All right, so this is always going to be a unit vector multiplied by a magnitude, and so I can always rewrite it in terms of directional angles and a magnitude. So if I have my vector v, again, same vector, and the magnitude we've calculated multiple times now. And we're using, right, we have a nice magnitude here. A lot of times these end up with square roots, but I wanted to use nice numbers. I can then write this, all right, in terms of the direction, and I can rewrite v in terms of a magnitude of v and the directional angles, which we have already found as well. And cosine. And again, we like to write vectors in terms of a magnitude and a direction. All right, we have the direction identified, and this is about as specific as you can get. I actually have the angle off of the positive x-axis, positive y-axis, positive z-axis. I have the angle off of each of those, all right, multiplied by its magnitude. So this is actually a really clean form, all right, to write a vector in. Right? Even though, I mean, you might disagree and think that that's a pretty clean form. All right. That looks like a nice simple form. This is a descriptive form. All right. And we do prefer the descriptive form, especially in things like physics, and especially when you're trying to, it's too hard to visualize that. But knowing I'm 115 degrees off of the positive x-axis is actually more informative than -3. All right. So, again, vectors, good stuff. The other way to multiply a vector is a cross product. So, like I said, there are two ways to multiply vectors. Dot product, which is basically results in a scalar. The cross product results in another vector, which might feel like a more useful way. And that's true because when you actually cross two vectors, when you multiply two vectors, it should result in another vector. All right. The dot product is super helpful when determining things like, oh, what's the angle between them? All right. So it gives us information, but it doesn't actually result, right, in the finished vector. There's a nice simple rule known as the right-hand rule. When you have two vectors, all right, if you start, right, on the vector, and so order matters here, unlike the dot product, u cross v. Okay, so is different from v cross u, right? So the order now matters here. If I start with vector u, right, I take my right hand and I multiply it in the direction of v. Okay, so again, in order to actually use the right-hand rule, we have to be able to visualize where the vectors are. Luckily, we're pretending they're in the xy plane here. So I start with u and I cross it towards v. The resultant vector is orthogonal to the two crosses vectors, and that's the direction. So that's what u cross v looks like, right? It goes this way, right? Same thing. If this is the xy plane, u cross v, oh, it goes this way. And then if you do v cross u, start at v, head to u, it's still orthogonal, but the other direction. And basically the rule was always, if it hurts, right? If you're trying to, it's u cross v, but if I put my hand this way, wait, no, that hurt. It didn't, it's u cross v that way. Okay, so crossing the vectors results in an orthogonal vector. All right, the cross product is perpendicular to the plane those other two vectors sit in, wherever that plane may be in three-dimensional space. And you also should be familiar with this terminology, the normal vector, right, or normal force. Does that sound familiar? Huh? We've had physics, right? Never in your life? Oh my gosh, that is just tragic. Okay, well, you guys will have physics soon, I'm sure. All right, it's basically impossible to, okay. You didn't even have it in high school? What kind of high schools did you, that's just tragic. All right, so I was like, you might not, and even in high school, you might not have done that. But okay, the normal force is basically the force of any constant that sits there. All right, there are two forces acting on every single object. All right, this table sits here stationary. There are two forces acting on this. All right, the normal force is basically in this direction. In the opposite direction, what forces goes this way? Gravity. And by definition, everything equal and opposite reactions, right? One of the fundamental laws of Newtonian physics. All right, you have two forces with any stationary object. The normal force and gravity. Does that sound familiar? I was like, if you watch any, did you guys not even watch Big Bang Theory? I mean, come on, like I was like, yeah, I feel like on TV shows you could pick up a little bit. So I love watching Big Bang Theory because I'm always like to Ashley while we're sitting there. And in the background, like I watched the making of it, they have an actual physicist in there, and he writes the formulas. And I'm like, oh God, Ashley, I was like, they were doing like a third dimensional differential equations back there. And she's like, oh my God. And I was like, no, that's real math. I was like, that's an accurate equation. And I was like solving it and verifying to make sure they didn't make a mistake. I was like, at least that's good stuff. I was like, they did it for us nerds who were like, they're talking in the front, in the foreground, and I was like looking in the background at the equation, making sure it was proper. Okay, so anyway. Okay, so there is a formula here. Okay, this is not how we actually solve cross products. Cross products use matrices, and we're going to go through an example of how we do that. Cross product also, the properties, much more complicated than dot product. Everything you expect would happen with a dot product that basically happens with normal algebra you've already seen works. Cross product, and the biggest one is that order matters, which is kind of counterintuitive to a lot of our algebra, right? 5 plus 7 is equal to 7 plus 5. That's not how cross products work. Because we just talked about it. U cross V is one direction, V cross U is the opposite direction. Now, all the values would be the same. That vector is in the same thing, but they're all negatives, right? They're all the opposite sign of whatever they were in one direction. The other nice fact about cross products, so the dot product, we identified that U dot V, if that equals 0, the vectors are perpendicular. If U cross V equals 0, they're parallel, right? What are the two biggest things we care about lines? Are they perpendicular or are they parallel? Well, we have two very nice formulas, right, that identify that, all right? Dot product 0, perpendicular. Cross product 0, parallel, right? If neither result in 0, then they're neither, all right? And it is that simple. Okay, something else. So some facts. I cross J, that is the unit vector on the x-axis cross the unit vector on the y-axis. And this is what we were just talking about. If you cross the x with the y, what direction are you now heading? Z, all right? So you're now heading K, okay? And vice versa, right? If you cross y with x, you're headed negative K, right? And so these are nice, actually, properties, right? This is what we want because everything is perpendicular. A cross product results in a perpendicular vector, and that's why the 0, right? If the cross product is 0, it's not perpendicular, it's parallel, it's lying flat. And along those lines, right? If you cross x with x, oh look, you get a parallel vector to the x plane, and y cross y, etc. Another nice thing is that we use, in order to find areas of a parallelogram, which actually is an equation that we don't have. We have rhombus, we have rectangles. Okay, parallelograms actually have complicated areas. Well, it's actually just the magnitude of the cross product. And we're going to look at that in a minute as well. So in order to do this, we need to refresh a little bit. All right, in order to do cross products, we need to refresh a little bit about determinants. So a 2x2 determinant. In order to do a 2x2 determinant, you multiply the diagonals minus the other diagonals. But we are going to be in 3 dimensions, so we need to look at 3-dimensional determinants. In order to do a 3-dimensional determinant, you take the first value, right, in the upper left, and then you make the determinant, right, by crossing out that entire row and that entire column, and then you have a 2x2 determinant that is resulting, right? And that's why it's B2, C2, B3, C3. Then I go down and the signs are rotating, right? Just like it's this minus this. So now I go negative the second value, right? And then I cross out that row and that column, and notice that one is a 2x2, B1, C1, B3, C3. And finally, All right, the last one, B1, C1, B2, C2. All right, so determinants, all right, are how we're gonna do cross product. Now, determinants work in any way, all right? And beware, your calculator does do this when you have numbers, but we're not gonna be able to do it when we get to cross product, so I'm gonna do it by hand. And determinants also have a nice property. So this was going down the row, but technically you could pick any row or column as long as you do it all the way across. And to that nature, because of how cross products with vectors work, I'm gonna go across the top row. So that means I'm gonna start with -1. And in order to look at this, I cross all that out, and my determinant is just this guy. So I have the determinant of 1, -1, 8, 1. Now, like I said, I'm gonna go across the top row. So that's my first value. I'm picking that as my second value. -0. What is the 2x2 determinant that remains?
-5, -1, 4, 1.
That is correct. All right, so again, covering up that column and row, and that's what results with the determinant. All right, then plus, and I'm using that last one. What's the determinant of this last one? Not Britta.
-5, 1, 4, and 8.
That is correct. All right, does everyone see how we're doing this? And again, in your calculator, and if you want, I'll show you how to do it, but we're about to have IJs and Ks, not numbers. So I want to make sure we can do this by hand. Because there is no computer calculation to do a cross product. All right, and then you simplify this down. Okay, so then it's 1 times 1, which is 1, minus 8 times -1, which is -8, minus 0, and it doesn't matter what's in here, plus 1 times -5 times 8, which is -40, and minus 4. Okay, so where are we? 9, -9, 0, and minus 44, so -53. Okay, so that actually resulted in a number. Nice, pretty, wonderful. Calculating cross products for determinants, all right, with vectors, okay? Along the top row, we actually put IJK. We determine our components, right? X, Y, Z. And again, our vectors only have 3 components each, so we weren't gonna be able to fill a 9 by 9. The cross product values actually then go along with, oh, that's the X component, right? That's the Y component, and that's the Z component when you make those mini determinants. But basically, and the order matters here as well. U cross V, U has to be the first vector entered, V is the second vector entered. If you do that backwards, then you actually did V cross U, okay? All right, so let's look at an example all the way through here. I want to find the area of a triangle determined by the points PQR, and then find a unit vector perpendicular to the plane PQR. Again, stuff that we have done, and now we're taking it to the next level and in 3 dimension. So here's the big thing. It didn't say that, like, again, and these are points in space. I have point P, Q, and R. So I need to start by making a vector. So how do I make my vector? I need vectors. I don't need points. So it all starts with, I need to make a vector. And I'm going to call the vector U, right? U, V, W, right? Those are the good ones. The good news for us is you have to pick a start point. And as long as you pick the same consistent start point, that's all that matters. I don't want to pick PQ and then go R to P. Okay? So I'm going to go P to Q for one of my vectors. I'm going to calculate that in just a minute. And while I'm at it, I'm going to pick my other vector just so I don't screw this up later. And I'm going to go P to R. Okay? This notation indicates that I started at P, went to Q. I started at P, went to R. Okay? So I've created in space Here's my point P, here's my point Q, here's my point R. All right? That's basically what this looks like. This is somewhere in 3 dimensions though. But it doesn't matter, all right, as long as we have that concept. Okay, then in order to do it, and I'm going to put this in a vector component form. So then top point minus the bottom point. Okay, so 2 minus 1, 0 minus -1, -1 minus 2. And the biggest thing with these is, remember, it's the end point minus the initial point. And the signs are what always screw people up, especially something like this one, 0 minus -1. Make sure that you always have the subtraction in there, then put the point in. All right, way too often, all right, I see, I mean, the math that we're doing, is it difficult? No, but these sign issues will crush you, okay? So just be careful. All right, so what do we end up with here? 1, 1, -3. And similarly for P to R. So 0 minus 1, 2 minus -1, 1 minus 2. Okay. All right, so we have our 2 vectors. And I want to find the area of the triangle determined by the points P, Q, R. So above, we found the area of the parallelogram. The area of a parallelogram, okay, is the cross product with magnitude of the cross product. But notice that a parallelogram looks a lot like a double triangle. If you cut it here, that is, we find half the area of a parallelogram. Is that equal to the area of a triangle? Yeah. So I can expand that formula, and basically what I need to find, since I want the area of a triangle, that is 1/2 the magnitude of U cross V. That means I need to do U cross V. One, -3. Okay, so now the cross product, all right, with I, J's in case. So I. And the good news, the term out front is always your the components I, J, K. All right, that results in what determinant? Charlene.
1, -3, 3, and -1.
That is correct. Okay, good. So we're pretty good at this. All right, minus J, and don't forget that that sign is also easy to forget. Then this results in what determinant, Macy?
Do not know.
All right, so J means cover up that column and that row, what's left?
So 1, -3, -1, -1.
Yes. Plus K. And then Jada, what determinant for K?
1, -1, 3.
Say it one more time.
1, -1 and 3.
Okay, yeah. And then calculate those away. And again, they're just mini determinants. 1 times -1 minus 3 times -3. And you end up with And we will stop there. We'll finish this example next class, since we're getting close on time and I want to talk about some other stuff. I don't want to rush it. All right.